everyone, I welcome you to yet another lecture under Concept Clarity lecture series by Clarity for Sure and Agriclarity platform. And today's topic of discussion is problematic soils. Okay, so yes, it is another important topic from the soil science for both AFO and NABARD. So let's just start with our today's topic, problematic soils. So problematic soil is a soil with the physical, chemical, and biological constraints. Okay, like extreme pH, salinity, sodicity, poor drainage, or toxic elements. Okay, so we know that we call soil as a healthy soil when it has a optimum pH range, that is 6 to 7.5. When the salinity is under control, it is less than 2 decimol per meter. When there is proper drainage, proper infiltration of water, when all these conditions are there, then we call it as a healthy soil, right? But when there is a deviations from these particular important parameters, that is extreme pH, salinity, sodicity, poor drainage, and the presence of toxic element, then we call it as a problematic soils. Okay, it is going to create problems for plant growth and cultivation. Okay, so yes, and these problems are created because of the presence of chlorides, sulfates, carbonates, and bicarbonates of sodium, calcium, and magnesium. Okay, and these all chemicals are present in excess. They are present more than they are needed, and because of which soil becomes saline and alkaline. Okay, there will be a disturbance in the pH, which is not good for our crop and develop for our crop. Okay, so for the management purpose and for study purpose, we divided these problematic soils based on the soluble salt content present in that soil, exchangeable sodium percentage of that soil, and pH. Okay, on these three parameters, we divided or classified soils into different groups. First is the saline soil, second is the alkaline soil, third is the saline alkali soil, and fourth is the acid soil. Okay, so let's just study all these soils one by one. So before that, let's discuss this ESP and soluble salt content. Okay, so let's see what these terminologies are. Okay, because they are important for you to understand the classification. So ESP is exchangeable sodium percentage. Exchangeable sodium percentage. So what is this? So this ESP is a measure of amount of sodium held on soil's cation exchange site. Okay, so okay, let's see first cation exchange site. So what is cation exchange site? So cation exchange sites are negatively charged surfaces on soil particles, mainly clay and organic matter, that is humus. You must have known that this clay and organic matter possess a negative charge. Okay, and they are present on the soil particles, and when these negatively charged surfaces attract and hold positively charged ion, then it is going to be called as a cation exchange site. Okay, so this is a soil particle. Let's suppose say there are a negative particles present, that is humus and clay, and these positively charged particles like calcium, Ca2 plus, Mg2 plus, Na plus, and K plus, these positively charged particles are going to be attracted by these negatively charged clay and humus particles, forming a cation exchange sites. Okay, so these cation exchange sites, I hope you understood the concept. Okay, so what is the reference of these cation exchange sites in the ESP? So the ESP is a measure of the amount of sodium held on the soil's cation exchange site. As I said, these are the cation exchange site, and these positive cations will be held on these exchange site. So the amount of sodium on that exchange site will be calculated in this ESP. Again, let's read the definition again. So ESP is a measure of the amount of sodium held on the soil's cation exchange. We are just calculating the amount of Na plus present on these exchange site. Okay, and to relative to the total cation exchange capacity. Let's suppose if it is 100, then out of 100, how many Na plus are present in on those complexes that we need to find out. I hope you understood. Okay, so it could be okay. So ESP could be high or it could be low. So when the ESP is high, that is more than 15%, its impact will be poor seed germination, restricted root growth, toxicity of Na plus, because Na is present more, right? When it is more, then it will cause a toxicity which is not desirable. The nutrient imbalance, because Na plus is present more than these other cations, which is not good. We need a balance of all the nutrients. But high ESP is going to create a nutrient imbalance and reduce yield. It is not good. High ESP is not desirable for us. Okay, so please keep this in mind. High ESP is not desirable for us. Okay, it will make soil sodic. It will make soil sodic because of presence of Na plus. Then poor structure due to dispersion of clay. Please note it down. Please note it down that sodium is called as a dispersing agent. Okay, it is called as a dispersing agent, and Ca plus and Mg plus are flocculating agents. Okay, and the presence of these presence of Na plus is going to create the dispersion of clay and also the organic matter. Okay, so please keep that in mind. Next is the crusting and swelling. Swelling, and reduce permeability. Okay, this dispersion will cause clogging of the pores, reducing the permeability and infiltration of water in the soil. We will see that in the next slide, but just remember these. And the pH will be more, that is 8.5. Again, I am telling you that the high high ESP is not desirable for us. Okay, and the low ESP is less than 15%, which is good, which is good for crop health, which will be good for efficient water and nutrient uptake. There will be no sodium toxicity. There will be balance of all these cations on that cation exchange site. Okay, and there will be no significant clay dispersion. Okay, so yes, this is what is the ESP. It is the amount of sodium held on the soil's cation exchange site. Okay, next concept is EC. Okay, electrical conductivity. So this again is important part, and again the questions and PYQs were there from these EC concept. Okay, so please let's understand what is EC. So EC is electrical conductivity of a soil and is a measure of its ability to conduct an electric current. It's easy, right? Electrical conductivity means its ability to conduct the electric current, which is indirectly indicating the presence of soluble salt. Okay, so because there are more number of soluble salt present in these soil, it is going to have a high EC. That is, it has a capacity to conduct the electric current. I hope you understood my point. That is, high EC means high soluble salts, low EC means low soluble salts. Okay, and the unit of EC is a decisiemens per meter. Okay, and high, that is the EC level more than 4 decisiemens per meter means high soil salinity, which is going to disrupt the plant water relation due to osmotic pressure. We will see this concept again in the coming slides, but again high EC is not desirable for us because it is going to create osmotic pressure, and the low is good, healthy for a plant growth. Okay, this high ESP is not good, high EC is not good. ESP is the amount of sodium held on the soil's cation exchange site, and EC is the ability of that soil to conduct electricity, which indicates the presence or concentration of soluble salts. When the soluble salts are more, it is going to carry more electricity, that is high EC. When the concentration of soluble salts are less, then it means it will not be able to conduct the high electricity, which means low EC, which is good for the crop. Okay, So yes, these were the two important concepts. So let's start with our first soil, that is a saline soil. Okay. So saline soil contains excessive soluble salts, and we seen just now the concept electrical conductivity. If the salts are excessive, which means you only tell me the EC will be high or low. So EC will be high, right? Because of the presence of soluble salt, it will be able to conduct the electricity, because of which the EC, electrical conductivity, will be high. I hope you got my point. So saline soils are the soil which contains excessive soluble salts, mainly chlorides and sulfates of sodium, calcium and magnesium. It is not just sodium, calcium and magnesium. Okay, all salts, chlorides and sulfates of sodium, calcium and magnesium, which hinders the plant growth by creating osmotic stress. So what is this osmotic stress? Okay, just relate the one concept. You must have heard about the fish salting. You must have heard about the fish salting. For the preservation and long-term preservation of these fishes, we salt them. We dip them in the salt solution, and what happens, the moisture which is present in the body of the fish will come out of it, and it will be like there will be no moisture in the body, because we dipped in the salt, so the concentration of salt is high outside the cell of the fish, and because of which the water which is present in the body of that fish will come out, making it dry, and it will help us preserve that fish for a longer time. That is the same what is happening here. Okay, that is what is happening here. So let me just, so these are the roots. Okay, these are the roots, and let's say this is the cell of the root. Okay, so when these soluble salts are present, what is happening? It will disrupt the water potential which is necessary for flowing of water from one moment to another. Okay, and the presence of salt, high concentration of salt outside the roots cell, will cause what? Will cause this water to come out of this cell, which is not good, making these cells dry, making these cells water deficient. Okay, and disrupting the intake of water, because the salts are present in high concentration outside the root zone. The water is going to flow outward and not inward. Okay, so this is what is happening. It will create the osmotic stress, making the moisture flow reverse, water flow reverse, which is not good, and it will dry out the roots, or dry out the crop. Okay, so this is what is the effect on the plant. Poor germination, stunted growth, because they are not getting enough water. Reduced water uptake, as the water is flowing reverse, right? The water movement is reversed because of the high concentration of salt outside the root due to high osmotic pressure. And no severe, okay, there is a no severe dispersion of the soil particles. Let's keep this point for latter. Just remember, poor germination, stunted growth, and reduced water uptake. Okay, so EC is more than 4 decibel per meter, but ESP here is a low. Okay, because this sodium we see in ESP was the presence of sodium on that exchangeable complex, cation exchange site, right? But here this sodium is soluble, it is a free and not bind on that exchange site. Okay, so and a presence of others, calcium and magnesium, will balance out all the process, and because of these reasons ESP is less than 15% and the pH is less than 8.5. Okay, so how to manage this soil? So management practices: leach out, as these soils are soluble. It is possible that after application of irrigation water, those salts will be soluble in that irrigation water, and they will leach out with that water with the proper slope. Okay, so for this we need a proper improved drainage system to leach out all the soluble water from the field. Okay, then growing salt tolerant crops. There are some salt tolerant crops like barley, cotton, which can grow in these kinds of extreme condition. You can opt for those. Okay, avoiding avoid saline irrigation water because it is going to worse the situation further. Just avoid it. Okay. Next, apply FIM, green manuring, and next is use of acidic fertilizers like ammonium sulfate. It will balance out the pH and it will make the soil better for crop health. Okay. So yes, this was a saline soil. Okay, so next is alkali or sodic soil. So soils that contain excess exchangeable sodium on cation exchange sites leading to dispersed soil structure, poor permeability, alkaline pH, which severely restrict the plant growth. Okay, so you only tell me if there is a excess exchangeable sodium on a cation exchange, what will be the value of ESP? It should be more than 15, right? We see in ESP was the amount of sodium on with respect to the total cation exchange capacity. So if there is excess exchangeable sodium, then ESP should be more than 50. As it is bind on that exchange site, the EC, electrical conductivity, will be less because it is not in the soluble form, you can say. And if it is not, salts are not soluble, electrical conductivity will not be that good. So these are opposites. Okay. And pH, the value of pH is more than 8.5. So why here we are saying dispersed soil structure? So as I already said, so sodium is a dispersing agent. Okay, and when there is excess exchangeable sodium, because of high amount of concentration of sodium, the soil will be dispersed. Okay, the soil, the clay, organic matters will be dispersed, leading to formation of the structure like this. They are going to clog the pores which are necessary for the infiltration of water, leading to blockage of water, poor permeability. The water will not infiltrate below. This is crumb structure, right? This flocculation will allow the permeability, good permeability of water reaching all the root zone. But here you can say because of the dispersed structure, it is going to clog the pores, leading to poor permeability. Okay, I hope you got my point. And these alkali soils will show black alkali patches, a greasy surface due to dispersion of organic matter. Okay, and it will lead to poor seed germination and root development, nutrient deficiencies, especially calcium, zinc, iron, and toxicity of sodium and carbonate ions because of the excess exchangeable sodium. Okay, how to manage it? So apply gypsum. What will happen when you are applying gypsum? This calcium will replace this sodium on that exchange site and will balance out the total cation exchange capacity. Okay, reducing the concentration of sodium. It will improve the soil structure, will allow the flocculation. As I said, calcium and magnesium are flocculating agents. It will again create this good soil structure by replacing that sodium on exchange site. Okay, so apply gypsum to replace exchangeable sodium. Then you can also go for sulfur, sulfuric acid, iron sulfate, iron pyrite, molasses. Then ensure proper drainage again to leach the sodium. Add a green manure and deep ploughing. Deep ploughing to improve the water movement. For this soil, you need to do what? Do a deep ploughing. It will invert the deeper layers and will flocculate the soil. Will increase the porosity, which is good for water movement, right? So yes, please note it down that this management practices are important. These management practices are important. They are going to ask what is the management practice for alkali soil. So the addition of gypsum or iron pyrite or iron sulfate is the management practice for alkali or sodic soil. So please keep this in mind. Okay. Next is the saline-sodic soil. So this is like the worst condition because both the problems are combined here. Okay, soil that contains both high levels of soluble salts and high exchangeable sodium. The soil is called as what? Saline-sodic soil. So both problems are combined here. Like it is like buy one get one free. Okay, there will be high soluble salts and there will be high exchangeable sodium. on that cation exchange sets, combining problems of saline and alkali. So you only tell me if there is a high level of soluble salt, EC will be what? EC will be more, because soluble salts will conduct more electricity, so EC will be more than 4 dm per meter. If there is a high sodium exchangeable percent on that that complex, then ECP will be more than 15%. I hope you're getting my point, what I'm trying to tell. And the pH is less than 8.5. Okay, here both are more, which is not good. As I said, we don't want a high, and for that reason it is called as a problematic soil, right? So why the soil is formed? Okay, the reasons for formation of saline-sodic soil is low rainfall, high evaporation, make so leaving water from the surface, but salts will be accumulated there, increasing the concentration of salt. Okay, poor drainage, again because of poor drainage they will accumulate. High water table will bring those salts up in the surface, right? Then overflow of seawater over the lands, irrigation with saline water, salts blown by wind, saline nature of parent material, and excessive use of basic fertilizers will create the problem of saline and sodic soil. Okay, how to manage? So manage with the gypsum application, which will replace the sodium on exchange site. Leaching of both salts and displaced Na with the good quality of water, good quality of irrigation water is necessary. Okay, and improve the drainage system. So yes, this was the saline sodic soil, and the last one is the acid soils. Okay, so acid soil is the one with less than 6 pH, where hydrogen and aluminium, that is H plus and Al3 plus ions, dominate the soil solution, making the environment toxic for both the crops. So just remember the definition. When we are saying acid soil, there will be high concentration of H plus and Al3 plus ions will be there. Okay, and its impact is it will lead to deficiency of nutrients like phosphorus, calcium, magnesium, and molybdenum, and toxicity of aluminium, manganese, and iron. Okay, now how to manage these acids? So liming is best for this. This is important. You can expect questions from this, that how to manage the acid soil. So by liming, application of limestone, dolomite, or basic fertilizers like NaNO3 or basic slab will improve and increase this pH to optimum level, right? So yes, this is what is the acid soil. So yes, in conclusion, this is what you need to take from this lecture. Okay, this is only important, or I guess most important part of this lecture. Okay, here, as I already said, there was a paragraph based 2-marker question in the NABARD from this chart, and this is really important. This is only you need to take, okay, and revise it before your exam. You will be good to go. Okay, so saline soil we already covered. Saline soil have a high percentage of soluble salt, which means more than 4 EC, right, and less than 15 ESP. And alkali soils are the soils with a high exchangeable sodium on that complex, right, for which ESP will be more than 15, and as the sodium is not in the free or soluble form, the EC will be less than 4. And saline alkali is the combination of both the problems. So there will be high soluble salts and there will be high exchangeable sodium. Okay, so both will be more. And the pH, you can remember that saline is less than 8.5, alkali is more than 8.5, and saline alkali is less than 8.5. So yes, I hope you got what I was trying to say, and you understood the way of my teaching. And yes, so this is the practice question for you guys. Just try to attempt it and comment down below if possible in the comment section. And yes, do consider our IBPS AFO test series by Clarity for Sure. You can go and visit Clarity for Sure portal for the test series for AFO. And you can also visit our Telegram channel. The links are in the description. Okay. Thank you so much for watching. See you in the next session.